Okay guys, in this video we're going to look a little bit about what it means for two matrices to be equal. Okay, matrices being the plural of matrix. So we say matrix equality, two matrices can be equal if and only if. Okay, so if and only if they have the same dimensions. That is, the same dimensions means they have to have the same number of rows and the same number of columns or the same order. So we say equal entries in corresponding positions as well. So they have to have the same dimensions, but also equal entries in corresponding positions. And so that is to say, as we look down, say, at this equation that you see here, it looks like we have two matrices. First thing I want to check is that we're committing to the fact that they're equal, but that must mean that they have the same number of rows, same number of columns. So let's find their orders. I notice that this has a two-row, three-column arrangement here, and this also has a two-row, three-column arrangement where this last term here in the first row is just an expression. So we say 2 by 3. So 2 by 3, and these can only be equal, if this is what we're admitting in the first place, if corresponding entries are equal. So that is to say, if you notice, like, for instance here, the first row, second column entry here is the same as the first row, second column entry here. Or likewise, the second row, second column entry is the same as the second row, second column entry. Or for instance, the second row first column entry is the second row first column entry over here. But you'll notice that in some of these places, sometimes you've got included variable values. And so because we already are assuming that these are equal, so we say assume equal. Since we're doing this, then we can say, well, since everybody in corresponding parts are equal, then I could say with 100% accuracy that the first row, first column entry in the first matrix has to be equal to the first row, first column entry in the second matrix. So one thing that I can already conclude is this: 5 must be equal to y. And I'm actually going to put a box around this and say, well, then I've already discovered the value of y. How about x? Well, I notice that x here is in the second row, third column. So this x here must be equal to the second row, third column entry over here, which means that x has to be equal to 6. And then I've already got the value of x. And then last but not least, we say, well, I notice I had a z in here. And, you know, this was this expression z minus 4. Now look where it's at. We say it's in the first row, third column of the second matrix. Well, the first row, third column entry in the first matrix is 2. So we could say, well, then 2 equals that z minus 4 value. And so we do actually need to solve this equation here. It's not like it's very hard. We'll just add 4 to both sides. But we end up discovering that z is equal to 6. And so one thing that I want you to notice is if we were to rewrite this equation, okay, so like for instance, you know, we say 5, negative 2, 11, this was negative 1, this was a 2, and then we had an x here, and then we say this was equal to, well, y, I'm going to put blank parentheses, negative 2, 11, negative 1, and then we had z minus 4 here, and then 6. If I go back and I substitute in for z here, I'm going to put in 6, and then for my x, I'm going to put in 6. X was second row, third column, so 6 here. And then for my y value, which was in the first row, first column up here, I'm going to put in a 5. I want you to see then corresponding entries would be equal. So 5 is 5. 6 minus 4, well, that's 2. Well, 2 is 2. And then I also know that this 6 here has to be equal to this 6. So that being said, whenever we deal with matrix equations, it's going to be often the case that you have unknown variables inside one of the matrices or both, and we want to solve for those unknown values. But the neat thing is that if we're going to solve for the unknowns, we can already assume that they're equal if this is what we've been told. So for instance here, I could say, well, you know, this negative 3x here, look where it's at. It's in the first row, first column. Well, the first row, first column entry over here is 12. So I'm just going to say, well, negative 3x and 12, if these matrices are equal, those have to be equal. And so, you know, just like we normally would with an algebraic equation, we can go ahead and solve this. But we could see that easily, if I plug a negative 4 back in right here for x, I get negative 3 times negative 4 is 12. Well, that's what this is over here. And so to finish this one off, I'd say, well, you know, this y here, y is in the same spot as negative 6. So, you know, y has to be negative 6. So pretty easy to do these. You know, you get a little bit more complex expressions as you look through more problems, I would suppose. But looking at something like this here, I would just encourage you that if you ever have an expression, go ahead and put parentheses around it, because it's kind of like the number that is in that spot, in that row and column. All of this is. So we say 2a plus 1. Well, this is first row, first column. Well, this is first row, first column. And if these matrices are equal, then these two things have to be equal. So 2a plus 1, now we know it would have to be 17. And again, just like we would with I guess, a normal algebraic expression, we would just go ahead and solve this using inverse operations. And we say, well, then we would discover a is 8. And likewise, we would say, well, this 1 right here and this b minus 3, these have to be equal. So if 1 is equal to b minus 3, well, then adding 3 to both sides gives us the fact that b is equal to 4. So put a box around this. And then last but not least, we say, well, the 2c here and 10 are in the same position. So 2C and 10 have to be equal if these matrices are equal. And this leads us to the fact that C is 5. So again, easy to check these. Go plug them all back into all these spots, but you should end up with two equal matrices as we define them to be in the first place. Cheers.